Today we want to look a little bit more detail at the del operator, specifically applying it to vector field, the curl, resulting in the curl and the divergence. The del operator shows up kind of as the derivative in our fundamental theorems of calculus for vector calculus. The structure of a fundamental theorem of calculus says you integrate a derivative over a set by evaluating the function at the boundary of the set. And for vector calculus, the del operator is what stands in as the derivative. So the del operator said is this vector, partial with respect to x in the I direction, partial with respect to y in the j direction, the partial with respect to z in the k direction. We can apply the del operator to a scalar function like we do in the gradient, and we could utilize it as a vector in the curl and the divergence. So really our fundamental theorems of calculus, we have the gradient of f is just del f. Here we're applying the del operator to a scalar function, and the result is a vector, the gradient. The curl of f is the del operator and the cross product, excuse me, of the del operator and a vector field. So here, the curl of f, we're applying the del operator to a vector field. Taking the del operator and finding the cross product with the vector field. And the divergence is the del operator in a dot product with the vector field. So each of our fundamental theorems of calculus involve a different use of the del operator, standing as the derivative. I don't know how to speak in quotes and say the derivative, but that's referring to my general structure of fundamental theorems of calculus as integrating a derivative over a set by evaluating the function at the boundary of the set. Let's talk a little bit about divergence. So the divergence of a vector field will be del dot f. So we'll apply the del operator to a vector field and come up with a scalar. So we need some context for thinking about this. So we're going to imagine the vector field as the velocity of a gas. It would be like air flowing around the room. However, imagine the vector field as the velocity of some gas. Actually, let's start with just a calculation. Let's suppose we have a vector field that's going to be x squared y I hat plus zj hat plus xyz k hat. Del dot f will just be the del operator dot this vector field. So del dot f we'll take the partial with respect to xi plus the partial with respect to yj plus the partial with respect to zk dot this vector field. In a dot product, the dot product is just the sum of the products of the corresponding components. Here, we're not so much multiplying partial with respect to x by x squared y. And these aren't things that we would multiply. We're applying the operation partial with respect to x to x squared y. So instead of multiplying, we're applying the operator. So we take the partial with respect to x of this first the I component. This is going to result in a scalar function, which makes sense because when we find the dot product of vectors, we end up with a scalar. And in this case, instead of just multiplying the components, our multiplication is going to be apply the operator, do the operation. So here, the multiplication is to do the operation. So here, the multiplication is do the operation. So we're saying the partial with respect to x times x squared y. That means take the partial derivative of x squared y with respect to x. Doesn't look like our normal multiplication, but the partial derivative with respect to x of x squared y is going to be 2xy. The partial with respect to y of just plain old z is 0. And the partial of z with respect to xy is xy. No more I, j, and k because we're doing a dot product. We're going to end up with a scalar. Here is our scalar function, 3xy. The dot product is a scalar product. So we expected this to be a scalar function. This is a nice establishing shot for some kind of quiz or test or final exam. Like, oh, here's a vector field. Find the divergence of the vector field. And all you got to do is take some partial derivatives and add them together. This is how a 12-point problem starts off with a nice easy 4 points. You just have to apply the divergence, find the vector field, score 4 points. Then the other two parts make you think about the divergence. And you're like, well, I don't want to do the think about part. I just want to do the stuff part. In the math class, it's like, oh, once the problem is all set up, then it's easy. But oh yeah, once the math is done, then the math is easy. It's setting up that's the difficult part. But setting up is the part that we should be focusing on. Which makes it a real kind of a jerk move when you get into pre-calculus. And we start being mad and you can't set up problems. And then it becomes like people saying, oh, kids these days don't know how to change a tire. Teach your kids to change a tire? No. It's like, did you expect that shit to just be passed on in genetic memory or something? Is it like an instinct that you had? Yeah, it should be taught in school. Taxes shouldn't be taught in school because we shouldn't have to do taxes the way we do. So that's just going to be the big the big mystery until we decide that we don't want to do this anymore. Yeah, that's always the best. Anytime there's a multiple choice test, I'm just not studying. Like, I'll do it if you're gonna give me the answer. Why am I gonna study? You're gonna be telling me what the answer is. Well, you won't tell me what it is, but you're gonna be handing it to me. No, because I allow unlimited attempts. I know it's weird on some of the homework problems, there's unlimited attempts, and there's like some of the problems are multiple choice. And I didn't want to bother going back in and like figuring out how many choices there were and like subtracting one or something. All right. So we need somewhere to think about the divergence, something to think about with when it comes to divergence. So we're going to imagine the vector field as the velocity of gas. We've done this before. It's air flowing through a room. So thinking about divergence. So the vector field, we can imagine that the vector field is going to be the velocity of some kind of gas going around it. This room is big enough that when I close the door, I don't feel quite as trapped as another room. There's still it's like I still feel trapped and claustrophobic in the room, but not quite as much as some like if this room was half the size, I would not be able to close the door. So imagine the vector field as the velocity of gas in a space. So we can imagine this in 3 dimensions and in 2 dimensions. I guess we could imagine it in 4 dimensions if you're capable of imagining 4 dimensions. You can try explaining it to me. I don't know if I can imagine things in 4 dimensions. If you can, try to explain it to me. If I can't, then you don't need it. Not in a useful way. The divergence is going to tell us the rate of expansion of the gas. So if we think of the vector field as the velocity of the gas in the space, then the divergence will be the rate of expansion per unit volume under the flow of the gas. So imagine the divergence as the rate of expansion per unit volume. So it makes sense that we're calling it divergence. We're measuring how much the gas is expanding, or more specifically, the rate of expansion, how fast the gas is expanding. Since we might end up with negative values, we're doing a dot product. A negative expansion will just be compressing. So that would be the rate of the gas compressing. So divergence is expansion and compression. Let's look at some simple examples where we can picture a vector field and then imagine if the divergence is going to be positive or negative. So I cheated a little bit so I could draw stuff. Our space doesn't have to be 3-dimensional. It will be when we get the curl. But for divergence, we can just imagine things flat and just imagine another axis on it. So we're going to start with a 2-dimensional one that we can picture. This is because divergence is a simpler operation, so we have a chance of drawing it a little bit better. And we'll start with my favorite example of divergence. The vector field is just xi plus yj. Just use the x coordinate for the I component and the y coordinate for the j component. So just jumping over to Wolfram Alpha, our favorite calculating machine. Here's our vector field, x, y. So side note, here's how to plot a vector field in Wolfram Alpha if you want a picture of it. You can just search vector field plots, and it'll give you some inputs that you can input. So I'm inputting the vector field x, y, and we can see that this is just kind of all the vectors pointing away from the origin. So here's the origin. Along the x-axis, everything's just pointing directly away. And on the y-axis, things are pointing directly away. Oh, right. I'm just drawing a worse version of the picture we were just looking at. But by drawing this, we can see everything moving away from the origin. This gas is expanding. So we would suspect that the divergence should be positive. So we think the divergence looks positive because it looks like this gas is expanding. If we calculate the divergence, that means we should get a positive value. Remember, we're going to get a scalar. So the divergence of F, del dot F, will be the partial with respect to X of the I component and the partial with respect to Y of the J component. The partial with respect to X of X plus the partial with respect to Y of Y. So it's going to be 1 plus 1, which is 2, which is positive, as we had foreseen. Our intuition is that the divergence is positive, that this looks like that is expanding, and at every point, everything is like moving away from the origin. And here is the calculation confirming that. Not just because at the end it says Q, it says the rate at which we're moving in the X direction is positive, the rate at which we're moving in the Y direction is positive. This is all positive. So if I reverse the direction of everything, if I just take our expanding gas from this example and multiply by -1, just make everything go the other direction. Like just take this and turn everything back, turn everything around. So everything's going to be coming back. Here, it looks like the gas is compressing, so we expect the divergence to be negative. This is just based on our intuition of what we think is supposed to happen. And then our calculation will confirm this. So let's do a calculation. We're just going to take this and multiply by -1. So what is the partial with respect to x of -x and the partial with respect to y of -y? -1 -1 is -2, which is less than 0. That indicates negative expansion, which is compression. Yes. It depends on the vector field. If we have a more complicated vector field, we can imagine one point where everything's running away from that one point, and another point in another place where things are getting pushed to that point. So it could be expanding one place and compressing. It wouldn't happen here because our vector fields are super simple. Look at our vector field or our dot product. Our dot product was a constant. So nothing interesting is going to be happening. That's why I picked these examples. But take a look at our previous example. Our previous example, our divergence was 3xy. So we're going to have positive values if x and y have the same sign. In the first and third quadrant, we'll have positive values. So we'll, this is in R3. It's fine, it's fine. Where x and y are the same sign, we'll have positive values. You can see expansion. But where x and y have different signs, we'll see negative values. So we'll see compression. That would be point dependent. It didn't matter here because our divergence was constant because our function was linear. So I'm sure everybody was super suspicious when I picked such simple functions, but I wanted to draw it so we could see the expansion or see the compression. One thing to note is we could have neither. Let's do things in the other order here. Let's calculate our divergence to see what's going on here, and then see if we could see that happening in the vector field, which hopefully I preloaded in Wolfram Alpha. So we'll take the partial with respect to x of x and the partial with respect to y of -y. So of a 1 and a -1, 0. So our divergence is 0, which would indicate that our gas is neither compressing nor expanding. Let's look at a plot of this vector field and see if that's if we get that. I gotta wait for the zoom toolbar to go away because I can't remember which one it is. Oh, here's a graph of compressing. And here's the one. So we see when we're in the third and fourth quadrants, all those arrows are kind of pointing up, but bending away from the x-axis. So it's flowing towards the x-axis, but it looks like the x-axis is like a wall, and stuff is spreading out on either side of the x-axis. And then the mirror image of that is above. In the first and second quadrants, all the vectors are flowing down towards the x-axis and then spreading out when they get there. So our flow of this vector field is that we're on the y-axis, we're flowing towards the origin, And then on the x-axis, we're flowing away from the origin. So as we're moving up towards the x-axis, we're trying to bend, kind of bending away. And that's why these are getting flatter as we go along. And then the mirror image is that's happening above. So we're not getting expansion or compression. Question? Not really. What we need, all we need here is, so it, notice that the examples that we've had so far don't really care about the values of X and Y. We're just seeing things not expanding and not contracting. Like that's kind of what we're going for. Like even if we pick some other place away from the origin, even if we pick like a place over here, we see that the gas will be compressing because we have, as we get closer to the origin, the vectors are getting smaller, right? So there's a lot coming in and then a little less, they're smaller coming out, right? So even though there's flow in and out in that spot, when they come in, they're getting more, they're getting more compressed when they're coming out. I think that made sense. There's a lingering doubt in my mind, but here, wherever we look, there's flow, but there's no place where, there's nowhere where the gas is compressing in or expanding out. It's flowing along, but it's not compressing or expanding. So what does this have to do with our fundamental theories of concepts? We know we can interpret this divergence about vector fields expanding. We're imagining gas expanding. Let's tie this to our fundamental theorem of calculus, which says if we look at the divergence of a vector field in a space, at every point in a space, we can calculate this by evaluating the vector field at the surface. So if we look at all the expansion throughout, look at the expansion throughout the solid, at every point in the solid, we can calculate that just by looking at the vector field, how it flows through the surface. So on the left side of the divergence, we've got the gas expanding all throughout the space. How the gas is expanding at every point in the space. And we can measure this by looking at the vector field just flowing through the surface. Here we're measuring the expansion of the gas at every point in this solid. On the other side, we're measuring the vector field flowing through the boundary of that solid. calculating the expansion of the gas at every point in the solid. And on the other side, we're calculating the effect of the gas flowing through the boundary of the solid. What's going on at the boundary is informing us as to what's going on inside. It's very similar to our fundamental theorem of calculus when we're just dealing with position and velocity. Velocity as the derivative of position. How fast we're going at all these points will tell us how far we've gone from one endpoint to the other. How fast it's going tells us how much things are going. Remember, we think about the gas flowing through. This will tell us the rate of flow. This will be the flux of the gas through the outside. That the gas coming out of the outside tells us how fast it's expanding on the inside. Any questions? I know we haven't done any actual calculations with this because I don't want to do the calculations before we have this in mind. It's different when we're back in top one because we have a better understanding of position velocity. We have little gauges in our vehicles that tell us about velocity and position. We've got position meters and velocity meters in our vehicle. And we know that if we go faster, we'll cover the same distance in a smaller amount of time. We're doing the same kind of thing here, but we have to change our frame of reference. And as we saw with line integrals, the calculations get a little bit messy and you forget what you're doing. You know what I mean? It's like when you go after certain metrics, you start using metrics to gauge how you're doing. Then you decide what the metric, what direction the metric has to go to indicate improvement. Then you start chasing the metric and lose sight of what the goal is. Anybody work fast food? Does anybody notice that there's a timer? There's a timer that says how long the car has been there because they want the customer to be waiting for the food less. But has anybody been to the drive-thru where they said, "Could you go wait over there?" That's to reset the timer because they're chasing the metric. They're not getting your food faster, but they can say customers are getting the food faster because they look at the metric and say, look, now look at our metric, it's going faster. But it's taking longer for the customers to get their food because they put you in a holding pattern. They reset the timer rather than just reset the timer by giving you the food. So rather than possibly learning something about an inefficiency, they just game the system. Make sense? And the same thing happens when you have a problem on homework where there are 5 choices and you're like, well, I have unlimited guesses. I'm going to get my point. But instead of taking the opportunity to learn something, you're just like, oh, fuck it, just game the system. A, no, B, no, C, yes. That's how you could tell I didn't write the problem. If it's the choice is C, I didn't write the problem. Because if I wrote the problem, the choice is never C. Because people think C is the average of A through E. And I think that's dumb. And I'm like, I'll knock it off. Yeah, I think one of the reasons you go for 4 choices instead of 5 choices is so that there's no middle choice. You have to commit one way or the other. It's like the what's it called? The Likert scale, where it's like agree or disagree, and they're like, I'll strongly agree, strongly disagree. You can't put neutral, because everybody would just be like, oh, neutral, 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 neutral. You know what I mean? And it's just like rating systems. There's rating systems that are like, oh, 10, like out of 10. There's no point in having 10 out of 10 on the rating system. Because the way that the rating systems are used, if you mark anything other than 10, the company comes down on the employee. You could have 9s across the board, honest 9s across the board, where the customer is saying, there is barely anything that this person can do to make this experience better. And I don't think it would be worth it. And then the company would come to the employee and say, I see you've got all these 9s. Why not 10s? Right. Yeah. And it's not, and it's usually down to things that are beyond the employee's control, but they use that. That's why sometimes the employee's like, well, hey, I'm going to send you a survey. And they kind of imply that if you say anything other than 10, it's a bad review. Imagine if that's what was happening here. Unless you got it perfect on the first try, you flunk. You know what I mean? So, speaking of chasing metrics. Anyway. That's going to do it for today. Tomorrow we'll talk about curl, which is how things swirling around. It's just swirling around. That's it for today. I'll see you all on tomorrow. But have a good day, and thanks for